in the form of a message. Okay, now I think the recording has started. I need to acknowledge that, which I'm not sure how to do exactly because my mouse is hidden. Okay, now I have acknowledged that. Hope it's all fine. Can you still hear me? All right. Someone please say anything.
Yeah.
Very well. Okay, I carry on then. Right. Okay. So and contracts, they very much like objects can communicate. They can call methods and functions of other objects. So altogether, if you come from object-oriented world, this is a model of programming which is not entirely alien to you. And this is how people approach the smart contract programming and started to implement all this fascinating application. But then what happens if we are not the developers and we just want to interact with the contract according to its description, or something that is written on the web page that advertises the application implemented as a smart contract on Ethereum? Well, then we really need to be diligent and be able to read the code of the program of the contract to make sure that there is no some funny business. And so here is actually a contract with a funny business. So it has this additional function with a pretty descriptive name, steal money. And if someone doesn't read the contract, they actually do not realize that a particular client, a particular party on the blockchain, designated owner of this contract, can actually entirely deplete this contract of its money, like there is nothing. And this is unfortunately something that the users of the contract don't over realize, but the contract is just a piece of code that someone has written. And this piece of code is better provide the possibility to be audited. And this is the main target of one of the main targets of our work. So when the contracts started to be popularized by Ethereum, people kind of accepted the fact that they can be written in a high-level language, like the one we have just seen. This is a language called Solidity. But in fact, this is not how the contracts are replicated. So what is replicated is a much more low-level code because it allows for multiple high-level languages to compile to this code. So the contracts also must be Turing complete, which is a fancy way to say that they should be basically as expressive as ordinary programs. So anything we can express as a program, we should be able as a smart contract. So computer scientists call it Turing completeness. And that's because we really don't know what possible applications might be. So we better allow for kind of anything. So and finally, once the contract is deployed, we should act by it. But this is also something quite controversial because we have just seen the contract that has been stealing money. And if someone started to act with this contract, there is actually no way to revert this logic because that is something that is massively replicated and everyone has agreed that this contract should be there. So these particular givens of smart contracts, they also come with the shortcomings. So if the contract is written something close to the low-level language of our processors, like an assembly, it's very difficult to understand what in fact it does. It's not the nice high-level code that we have seen. It's something quite gibberish. So the Turing completeness actually makes it very easy to hide exploits in the contracts and also makes it very easy to write the computations that are difficult to reason about. Whereas the number of patterns when people can exercise smart contracts is not that particularly large. Finally, one should, if we consider the code as the ultimate law, one should be able to understand the code, to understand the contract. And we cannot really expect that everyone will come with the desire or even expertise to read the code of the contract. So we really need to build the tools that extract the essence of this contract. And again, doing that is difficult if your contract is written in a low-level language. So just to give you an example of things can go wrong, here is a perfectly fine contract that implements accounting. And some of you who have not been under the rock in the last 5 years might have heard about this big exploit called DAO, exploit for decentralized autonomous organization, when an contract of a similar kind was providing essentially two functions, to invest and to withdraw the balance, plus some other logic. But withdrawal was kind of funny because it was happening in a way that would allow to withdraw money once, but then before this contract has finished its execution, it would allow to withdraw it again and again and again until not only the initially meant amount was withdrawn by the third party, but also the entire contract would have been depleted from the money. And this seemingly pedestrian misunderstanding in how the contract should be interpreted led to the massive loss and one of the major forks, most known forks in the history of Ethereum blockchain. So given all these misgivings of the early contract model, my colleagues and myself, we started to ask ourselves a question: what's the right model of thinking about smart contracts? So, the model, thinking model that I'm going to propound here came from a very simple analogy. So at that time, I was working a lot on reason about concurrent computations. I was not at NUS, I was at University College London, and together with a colleague who was at NUS back then, Aquinas Cobor, we kind of noticed that there are lots of similarity in how people write applications that work over parallel architectures and applications that are typically executed by smart contracts. So in the gist of this analogy is that accounts using smart contracts on a blockchain are like concurrent threads using concurrent objects in shared memory. And by shared memory, we actually mean the replicated state on the blockchain here. So the idea is that so this analogy is useful because it actually allows to phrase many things that have to do with contracts, such as contract state, call and sending money, reentrancy, and other things as abstractions that are extremely well studied in the scientific community that has to do with concurrency. So for example, the issue of the reentrancy, so what allowed to deplete the DAO contract entirely from money, that is something that has been studied quite a bit in the concurrent design of algorithms, where you can constantly switch the context between the data structure and the one thread that operates with the data structure and some other threads that operate with exactly the same data structures. When you design these data structures in order to be used concurrently, you need to make sure that each particular thread always leaves the data structure in a particular safe state, which is described by some invariant. So whenever the thread picks up the structure again, it knows that it will not be subject of concurrent manipulation. And long story short, this is exactly what DAO contract has violated. So it actually didn't preserve this property between the manipulations by multiple, so to say, threads. So, this is something that allows us to build analogy. So here's another example, which is also very interesting, and it has to do with contracts interacting with the outside world. For example, there is a very common mechanism called an oracle. So if a contract needs to get the current forecast or the stock exchange rates, so it cannot really do that in one transaction because the contract is sealed to manipulate only with the state of the blockchain. So instead, it notifies another contract that implements an oracle. And this oracle will essentially send a ping to the third-party application outside of the blockchain that will get this information and will return it back to the initial contract by calling a callback. So from the perspective of the user of the contract, these two operations, asking an oracle and getting the response from oracle, should really be the same. But unfortunately, this is not how transactions on the blockchain work. So there is actually physical period of time between these two transactions, which can be observed. And what's even worse, these two transactions might be in different blocks, and quite a few things might happen in between. So if we are not careful to match this second transaction as a response to the first transaction, we might again find the contract in the state which doesn't expect this response at any moment. And in fact, there are quite a few contracts on Ethereum blockchain that violate this simple observation. So there is the game called Blocking, which likely was not super popular, which does exactly that. So it sends a query to an oracle, but when the answer comes, it actually might be an answer to a different query. And this altogether might result that the reward for the game will be transferred to a wrong party, which was not the actual winner, but that was someone else. All right, so now powered with this analogy, we try to exploit it in a white hat manner by writing a number of papers to detect these bugs and disclosing them responsibly. So with colleagues from the NUS School of Computing, we wrote this paper, and we also wrote this paper, which all use this idea, and the other researchers kind of also picked up this idea. So in the research community, this topic of finding bugs and smart contracts based on this particular analogy became very popular. But that's just about finding exploits. Can we actually do better? So can we avoid those nasty behaviors using better programming language design? So something that would not allow us to shoot ourselves into the foot in the multiple possible ways. And this is actually a goal of the modern programming language design, in particular to application for smart contracts. So facilitate reasoning about the high level behavior of our programs, which are the smart contracts. And the idea is that, so can we actually implement them in a way that they will be concurrent, but the concurrency would be slightly more principled than what Ethereum gives you. And this is how we came with the following prototype. So at that time, my main tool of work was this funny research framework called the Cockproof Assistant. This is actually a framework which is very good for prototyping languages, but also for prototyping frameworks to prove properties of programs in those programming languages. So you might or might not have heard of it, but Coq is actually one of the largest successes in the human-assisted formal verification, because it has been used with a great success to write fully verified compilers for C, operating systems, and distributed protocols, including blockchains. So what does it mean to have a verified compiler? Well, essentially, that's a compiler that never produces buggy code. And what does it mean to have an operating system which is fully verified? Well, that means to have an operating system that never crashes in any unexpected ways. And the same goes for distributed systems and protocols. So that means they do exactly what they're expected. And this is a lot of manual effort, but this is what the framework provides. So naturally, so this is what the code of this framework looks like. You are not expected to read or understand it, but the idea is that if you want to prototype a language for smart contracts, you don't need to build a compiler for this language or a runtime for this language from scratch. Instead, you can just write a bunch of definitions in Coq saying, well, your contract is a protocol, it has these fields, and then we are going to write a certain way to express what this contract can do, and then we can write certain properties of those contracts and try to prove that they hold or they do not hold. So in this case, what we try to do is to distill the essence of smart contracts. And the idea was that the contracts, they shouldn't be really thought of as objects. They should be thought as agents. So these state transition systems that interact with each other not by invoking the methods, but sending each other the messages such that each contract exclusively manages its own state. And the messages trigger the behavior, and the contracts might send more messages. But in fact, the state manipulation of the contract is quite minimal, and most of the logic happens by running the pure computations that actually do not change the state of any contract. So this is the paradigm known as functional programming. Okay, so the idea is that now instead of having the reentrant contracts, we can think of the contracts as a bunch of agents, and the first message is sent by the party outside of the blockchain. And then as a reaction to that, the contract might generate more messages that either go to other parties or other contracts, and then they can exchange these messages overall until either the whole transaction runs out of resources known as gas, or until all the messages are delivered and processed. Why this? Oh, sorry, I think I just accidentally stepped to the beginning of my talk. That's fine. I think I know where to go, how to come back. Right. So why this analogy with state transition systems or actors is so useful? Well, it's useful for the following reason. So now if each contract manages its own state and fields and only reacts to the messages, there's actually a very limited way one can screw up with this contract, because the only way to screw up with it is to send messages to it. And now what we can do is to basically consider all kinds of classes of messages that can be sent to particular contracts and try to reason about all the reactions of these contracts to these messages. And that's known as execution model. And this is just something that people in the formal methods field do. So they think about execution models and they think how to reason about those executions to prove certain properties. Okay, so for example, what would be a simple contract that fits this model? Let's talk about crowdfunding or ICOs. So these contracts has certain parameters with which it begins, like the deadline and its funding goal. It also has the fields which are supposed to be mutable, such as the registry of the accounts that back this contract. And finally, it only has 3 ways to manipulate with it by means of sending it messages: either donate the money, or get the funds if you're a dedicated owner of the contract after the deadline, and reclaim the donation if the goal has not been met. So now, once we have this idea of the contract and everything that can be done with it, we can start writing what's called temporal properties, which allow us to describe in the language of mathematical logics what are the properties that this contract should satisfy over its lifetime. For example, if the contract transitions from one of its state, which we call configuration, to another one, this particular logical expression says that if initially some property P holds, then eventually then Q holds at some point if the property R hasn't been violated before. Okay, I understand that this might be very, very abstract, but in fact, depending on the P, Q, and R's properties, very many reasonable things fit into this formulation. For example, token price only goes up. or no payments are accepted after the quorum is reached, or no changes can be made after the contract has stopped accepting the donations. So, but just by exercising these definitions, we can write lots of properties that we care about. And what's even better, we can write it in the language of this framework, the Cockproof Assistant, that allows us to prove them. So now we can take the statements which would be provided by the auditor in plain English, such as crowdfunding contract will always have enough balance to refund everyone. It will not alter the contribution records, and each contributor will be refunded the right amount if the campaign fails. For example, like where do these properties come from? Well, they come from either the specification of the contract in English, and this is where legal experts can interact with computing experts. So this comes from the legal expert, and computing expert translates that to the language of the mathematics formalized using the computer. So, and here's basically this very same statement, but now written using the logical formula encoded as a piece of code. And the nice thing, so now once this property is stated, it can be proven. So it's not entirely push the button. So there is some effort that needs to be done in order to convince the computer that this particular formulation of the contract satisfies this property. But the nice thing that once it's done, this is the power of mathematical reason. We know that the contract doesn't violate that. So we designed this language and this model with this idea of verification in mind, but well, it would be a theoretical proposal till the end of it if the opportunity didn't arise. So at that time, my current colleagues from School of Computing in the group of Pratik Saxena and Seth Gilbert published this very influential paper about the Sharding protocol for open blockchain. And this is something that led to the creation of the fintech startup that is now known as Zilliqa, and which has been very successful. So at that point, I was visiting the School of Computing and I was talking to these folks, and they suggested that it would be nice to have a language with secure guarantees, and would it be nice if we could collaborate. And turns out that the proposal that I had developed was a pretty good match for the systems that we have built. So at that point, there was a wish list of what properties this language should satisfy. And obviously, one of the main properties was safety. So the basic fault avoidance can be checked. Can be checked during the deployment. I think there's a typo here there. So also the language should be reasonably minimalistic, so not as difficult as EVM to formalize and maintain. Should be still quite expressive, so the common financial applications could be expressed in it. It should be friendly towards verification efforts, so it could be so we could actually transform these contracts into the models that we can verify and validate using the computer. And finally, it shouldn't be too bad in terms of performance. So we shouldn't pay the big price for all these safety guarantees that we have otherwise. So at this point, what was crucial is to understand what are the essence of smart contracts and what we need to retain in order to make a smart contract language and keep it realistic. So the smart contract should be able to perform simple computations such as arithmetic. It also manages its state, so it has certain effects such as sending, accepting money, and logging events. And finally, the contracts communicate with each other. And the interesting thing that something like Ethereum or EVM, it already allows you to do all of that. But all these four things, they are sort of intertwined. So if you want to think about the arithmetic computations of the smart contract, it's actually very difficult to do that in detachment of all other aspects, such as state manipulations or sending money or communicating with other contracts. So the one of the key design decisions for us was to build the separation of concerns. So whenever someone wants to verify and reason about how the contract adds numbers and whether it does it in the correct way, that's also can be done and formally specified. And if you're interested in the way the contract manipulates its state, that can be done over the mathematical abstractions of the computation. And finally, when we zoom out and we work with multiple contracts and the way they communicate, this is something that doesn't quite concern with the two other levels. So at this point, the contract essentially work as black boxes towards each other. And this is what the research in formal methods is very good to, is the separation of concerns. So we try to take the separation of concern and build a programming language around it. So that was the language that we have designed, and it's called Stila. So Stila turned out to be also a very beautiful town in Italy, or this plant, which is currently endemic in North America. But in fact, well, it mostly came as an acronym for a smart contract intermediate level language. So this is something that we hoped would be not exactly the language in which smart contract is written, although people now write contracts in it, but something that other languages can also compile to. Okay, so this language has been built on multiple foundational results from programming language theory. I probably won't have time to go on that. For example, it had like this very well-studied principled model of computation called SystemF. So it was not Turing complete. So it only didn't, for example, allow for infinite loops. It had explicit effects such as sending and receiving money and changing the fields. And finally, it embraced this idea of contracts being actors and working with each other by means of sending and receiving messages. Okay, so just quickly gloss over a bunch of slides to show you how small this language is. So this is the entire language. This is the entire definition of its types. You can probably recognize something familiar. So it has, for example, Booleans, it has maps, it has functions, and also has something that looks slightly more alien, such as this for all types, but this is essential to keep the language expressive while small. And this is pretty much 60% of the language that developers need to write. So this is a functional part of the language that has to do with computations and functions and applying them, and also the working with data structure. So it embraces lots of concepts from functional programming languages such as OCaml and Haskell, which are known to be very expressive. So you can write a lot of logic in very minimal amount of code. So the interesting part about smart contracts written in Stila that they don't have loops, but they provide somewhat more principal primitive, which is actually very easy to reason about and prove things by induction, called structural recursion primitive. So instead of writing a loop, what you write is a kind of a very obscure, okay, so it's a very obscure version of a for iteration. So basically it says what you should do when you finish iterating, what should you do at each iteration, and how many times you need to iterate. So the reason it's written this way, because it actually fits very well into the rest of the formalism. So there was no reason to introduce for statement if we have this. So for statement can be just added as a macro expansion over this syntax. So you can write some computation. So this is a literally Stila. It's a little bit verbose just because the language is small, but it's very easy to build a compiler from a more expressive language, very similar to Solidity. So that code wouldn't look that. So this is a function that computes Fibonacci numbers. Okay, I probably should not go into the details, but this is a simple function. So if you want to work with collections such as lists, we also do not provide loops, but we provide the way to iterate over the list. So if you want to do something with a list, typically you do something in the case if your list is empty, and then you iterate for the duration of the list, and then you take the list itself, and eventually you get the result. So this is actually a very general mechanism called fold. And again, you can express loops with it. So you see, it's like about keeping the language minimalistic while still possible to write all reasonable applications. Okay, so yeah, and you can write things using these functions. For example, you can write a function that finds something in the list, and it has lots of this annotation like A primes. But again, this is because Stila was meant as an intermediate level language, and in fact, those types are very easy to infer if you program in an IDE. Okay, now what about changing the state? So again, this fragment is very small. So Stila contracts cannot, like, don't do that many crazy things with the state. So they might assign variables, they might read from expressions, they can accept money, emit event, and send messages, and also throw exceptions. So that is pretty much it. Keeping it small makes it easier to prove theorems about the contracts. And finally, what exactly is the execution of this? So the execution assumes that the contract operates in the presence of its own state and also the state of the blockchain. And the result of its execution is the new balance, new state, and new messages to be sent to other contracts. So this is a fragment of the crowdfunding contract developed in Stila. It's actually quite simple to read if you know, like if you look at the right thing. So it takes the address of the sender and the amount to be donated, reads the current block number in the blockchain, makes sure that the deadline hasn't passed, and depending on whether the amount is right, sufficient, and came at the right time, it updates the array of backers and sends back the message. All right. So now the contracts themselves, they look like this. So each contract has a bunch of functions that don't change the state, but just essentially do the arithmetical computations. They're called pure functions. It also has the parameters, mutable fields, and a bunch of transitions, such as this donate, which we have seen. And this is actually very close to this model of actors that we have seen before, and we sort of understands the benefits on. Okay, so how these contracts were supposed to interact with the blockchain. So once the contract is written, the developers proposes the code of this contract as a transaction. And then if the consensus is reached on adopting this contract, this code is replicated using the consensus, and every participant in the blockchain stores its code. So once the contract is stored, other transactions might start interacting with this contract. And once the contract receives a message, it's being interpreted, it starts in consent message to other contracts. So unlike Solidity contracts, they cannot explicitly refer to another contract state. And that's what makes it possible to assert properties of contracts in isolation without assuming that they actually rely on other contracts, just out of their own definition and out of the messages. And there is actually quite a lot of code reuse, because most of the code written by the contract doesn't even assume the manipulation with their state. There are just computation that can be reused across the contract, and there is a mechanism for that is in the blockchain. So we had to do a little bit for the standard thing, which is called gas accounting, just to make sure, like, well, even though every contract written in Stila always terminates, we still need to control that the contracts cannot run forever. And there is this idea of assigning the cost to each operation. And this is something that the runtime of the contract tracks. So if the contract runs out of funds allotted for the transaction, the corresponding transaction with this contract will not be performed. So this is a standard mechanism that we took from Ethereum. There is absolutely nothing wrong about it. So we just took it pretty much verbatim. Okay, so the Stila interpreter, if you're really keen on doing some hacking, it's actually a really small code base, relatively, especially in its core part, if you don't count the infrastructure and the compiler and the frameworks around it. So initial version was just 200 lines of code of functional programming language UCaml, which is a very popular language in fintech applications. Company like Two Sigmas and Jane Street use it for writing high performance trading protocols, but they're also very popular for writing compilers for languages. So we use this language. It's written in a certain style that also makes it very easy to express the programming language concepts. And once we needed to add some changes as a response to how the protocol on which we deployed it evolved, it actually didn't require us to change the core logic. So the backwards compatibility and the forwards compatibility was quite nice. Okay, so that is about the design of the language. Now comes the interesting part. So once this language has been developed and we provided the runtime for it, how do we know that we make how do we know that we made the right choices? How do you know that this is actually a language which is good for a blockchain and is adequate for writing financial application, especially given that it has this very unusual things that I have demonstrated? Well, the first thing that you can evaluate language on, and evaluating programming language is a tricky part because usually it takes months and years. And you know, Python is older than Java, and it took several decades for Python to take off as a language until the humanity realized that this is actually a pretty good language for a particular class of applications. So, okay, how can we do it in a shorter term? Well, luckily blockchains are pretty vibrant environment, so things are moving really fast, and we could immediately try to implement certain applications in this language and see if its capability matches the demand. So we implemented the standard library, and in the very first few weeks, we implemented a number of contracts such as ERC20 for ICOs, ERC721, that's NFT, which no one really cared that much about back then, and now everyone, like, even, okay, so even my uncle knows what NFTs are, and also some games and some cryptographic primitives. So clearly from that case study, we assume that the language is expressive enough so we can release it into the wild and see what kind of crazy things people will do with it, or maybe not crazy, because that's our goal. So to control the amounts of craziness, we also wanted to make sure that taking these contracts, we can deduce something about them without doing full-blown audit, and also by using the power of computers. to enable the verification of the contracts. So for that, we built a framework to do what's called static analysis of the contracts. So the static analysis is a very well-known technique in programming which allows you to infer properties of the code without really testing it or running it, and do it in a sound fashion. So when the property is inferred, you know for sure that it holds, and it's not just something that is only true in a fraction of the cases, but it's true in all the cases. So the two simple instances of this analysis were the analysis that analyzes statically how much gas the contract will consume, and second is whether it actually uses the money consistently. So whether it doesn't multiply dollars by dollars, which doesn't really make sense, but adding dollars to dollars is fine. Okay, so the gas usage analysis is something that builds on the theory of like a simple complexity of algorithms, and it uses the standard mechanism that computer science students usually get in year one, but integrating with the language is not entirely trivial. So as a matter of fact, several years ago, I participated in a similar effort, although with a different goal for the language Haskell, working with researchers from Microsoft Research. Funny enough, none of them are now in Microsoft Research, but the language is still very much developed by them. Okay, so the idea of the gas usage analysis is that if we have a function, so how much gas this function will consume depending on the sizes of its argument. So here's a function that does something with the list. So clearly the amount of gas that how do I know that it's a function of a list? Well, because its type tells me that it takes list as a second argument. So clearly the amount of gas it will consume will depend on the size of the list. So we run our analysis, and we can see that the gas consumption of this function is going to be, well, okay, this polynomial 5 times a plus a times b plus 11. You might wonder, what is a and b? Well, the analysis also gives you a legend. So a is the length of the list, and b is a cost of calling the function, the first argument on the list. So altogether, the worst case complexity, which you can figure out from here, is proportional to the length of the list. And this is something that a first year good computer science undergrad would infer just by reading these functions, but now the computer does that for us. Will the computer be able to match the intelligence? All right, can you give me a second, please? I think my headphones just switched off. Okay, should be fine now, right?
Yeah, can hear you, Prof.
Thank you so much. Okay, yes, good that I've noticed. I hope I didn't speak. I wasn't without sound for too long. All right, good. Okay, moving on. Yeah, probably. Yeah, it's kind of scary to speak for several minutes and then realize that no one was really hearing, and you wouldn't hear anyone because the headset just switched off. Okay, I'm having a picture of Pratik stream. So okay, if that happens, so Pratik somehow let me know that something is wrong. Okay, good. Okay, so that gave us the analysis that inferred the complexity. So now what about the other analysis? So the analysis is more interesting. It's about not making non-trivial mistakes. So how to make sure that we do not miscalculate the money that our contract manages. And for that, we use this idea of cash flow, basically making sure that we can tell which parts of the state of the contract are representing money and which do not represent the money. And this is actually quite interesting because that didn't require any additional annotations from the developers of the contract. So this is just something that runs and infers that something is money and something is not, based on what initially interacts with the contract balance and what doesn't. And also, how do we check this analysis? Well, we ran this analysis against all these contracts and we derived the complexity bounds. And then we manually checked, and indeed those were all correct. So this gas usage analysis is actually a very useful tool to find inefficiencies
in your contract and also do some optimizations before you deploy it, so people actually use it. And the cache flow analysis is something that we just made sure that it works as it should on the known contracts. And again, this is a really great tool for finding bugs in the contracts prior to the deployment. So this is what's called verification, and this is something that we hope to enable, and to some extent we did. But there were, so that was roughly 2 years ago. Since then, there were more exciting development, which I will hopefully share sometime soon because it's still work in progress. Okay, so now what about the performance and the code size? So the contracts are not particularly large. They're slightly larger than the contracts in Solidity, but not by much. The performance was not that great initially. And when we looked at that, it realized that in order to cleanly separate the design of the language from the design of the blockchain, we had to basically sacrifice certain opportunities that would come from the more tight interaction that is done in Ethereum. Okay, so and specifically, there was a big overhead on reading and writing to the blockchain in the middle of the contract execution. So from that came a number of challenges. One of the challenges that has been addressed maybe like a year or a year and a half after we developed the first version of the language. And luckily, that's the challenge that didn't require change in Stila, but it only required a change in the runtime, so it was entirely transparent for the users of the framework, is to build certain machinery to support particular components of the state. For example, if we have our crowdfunding and we have this particular element of it, an array, keeping track of who donated the money, then this particular component can grow very large. And the larger it grows, the more difficult it is to maintain. So instead of reading and writing this whole array every time something happens with the contract, we implemented the protocol that would interact with the state of the blockchain in a very minimalistic way. So this fine-grained interaction, instead of reading and writing this array every time, it would basically bufferize the changes in it and apply them all at once. Okay, so this is just to show you that there was quite a lot of sophistication put into integrating this small language with the blockchain. And there were several other performance issues we have addressed, but luckily there were no known security issues so far. So that's okay. This performance is what we implemented by means of inter-protocol communication IPC protocol. All right. So enough with the technical stuff. Let's just talk about the big picture and where this language fit into the infrastructure. So luckily, since Zilliqa started the mainnet in 2018, so the smart contract language has been deployed in 2019, 2.5 years ago. So since there were hundreds of community contributed contracts, even more now as people are getting into NFT. So back then, there were mostly crowd sales, escrows, contracts for selling domains, access controls, a security token, and there were actually quite a lot of infrastructure that was built not by us, but by the community. So there was the language server protocol, Emacs and VS Code plugin, and quite a hardcore, and there were even third-party workshops. So okay, so this is from actually it's even from late 2018. So I cannot read what is written here, but I can see that this is a tutorial on Stila, which is really quite something, because this is something that warms my heart as a programming language researcher, because now I get to see people writing something in a language that also teaches them about how to reason about programs. Okay, so if you're interested, there is an IDE. It's actually very elegant and easy to try it online. And there is also a block explorer in Zilliqa that allows you to see the state of these contracts. So that was the story of getting a simple idea of building slightly more secure contracts and going all the way up to the deployment and to the adoption. And here I just cannot thank enough Zilliqa and my colleagues from NUS who are really open-minded and supportive in this change and provided a lot of resources and encouragement for this to happen. And this is actually something that is going on right now. But the talk is also about scalability. And here I just want to spend maybe a few minutes. I don't want to keep you too long, and also it will be fun to have some questions to talk about how exactly programming language design allows for scalability. So you see, when you talk about something like Zilliqa blockchain, one of the main components that comes to mind is its unique approach to L1 scalability, layer 1 scalability, where all transactions, they actually do not get processed by the entire system. Okay, I think I got a message from the chat. Okay, that's just hi guys. Good. Okay, so all transactions don't get processed by the entire system, but rather they are split into individual components where, so the whole system is split into individual components where transactions are processed by these components in parallel, but in a way that different transactions of different shards will not conflict. So altogether, it's like we just split the workload, but we didn't really introduce any conflicts or any overhead. And that works remarkably well when these transactions will just come chaotically, as on the left on the picture. They get distributed between multiple parts of the system called shards, and and then processed in parallel. Hold on. Yeah. Okay. So I'm just looking at the chat and no questions so far. Right. But what happens? So and this works well for transactions that just have to do with transferring money from one party to another. So what happens if the transactions involve smart contracts? Well, I won't bore you with the details, but this actually is a pretty difficult problem, which to date has not been solved in even systems like Ethereum, who are actively building the sharding support. So it is very difficult to run transactions on the same smart contract, such as crowdfunding, in parallel. Well, it turns out that the same idea that allowed us to build these summaries in terms of gas usage and money usage in the contract is also very useful for enabling parallelism. And the idea is that by analyzing the contract, we can know which of its transitions can run in parallel with each other or even with itself. So that means that we don't need to execute the transactions over even the same contract in the same shard. In many cases, we can put them into different shards. And that is something that we get by essentially having the contracts in the language that lends us this information. Okay, so in short, what happens is prior to the deployment of the contract, the programmer can also provide her intent to run some parts of this contract in parallel. And the compiler, or rather this analyzer, it will give suggestions on how this contract can be deployed in a way that certain transactions can run in parallel by producing what's called summaries. And those summaries are optimal in the sense that for the desire expressed, they give the optimal amount of parallelism. And then different transactions that manipulate with the same contract, they can go into different shards. So if you want some intuition, you can think of the crowdfunding contract where multiple parties can donate in parallel. And it's not like the donation of one party would prevent the donation of another party. So clearly we can just think of it as multiple points of donation, even though it's the same campaign and the same content. So that was the analysis that we built called the cost split. So that was actually integrated, not yet in production version. So that's still undergoing some testing, but we integrated into the proof of concept prototype. And it was very promising. So actually didn't add that much overhead over the processing of the smart contract transaction. So it was pretty like no more expensive than the other components, but then it gave some real speed up. So the plot that you have seen here is there are these bars showing how many more transactions we get to process per second, given the increased number of shards for particular contracts. So for example, the FT is the fungible token and its transfer. The number of transfers we can process, it grows proportionally to the number of shards via the system, which means more shards, more parallelism. And this is exactly what we want. And this is exactly what Zilliqa has been designed for, but it was a challenge to bring this design to smart contracts. If you want to have more details, so there is this paper, you can find it on my page. It's also on the it also will be in this video, and the main bulk of work has been done by my brilliant PhD student, Georgia Berla. All right, so to conclude, what are we looking for? So there are actually lots of exciting directions that we believe this technology has enabled. And currently, we are working towards translating Stila to Cock. It started from the Cock prototype, but now we need to come back to this route so we would be able to reason about it. So there is also quite a lot of excitement into building the compiler for this language to low-level architecture. So each miner can run transactions more efficiently. There are interesting challenges that come with it. And finally, it would be interesting if, along with contracts as the code, we could also deploy the proofs that the contract satisfy the property. So this would be even better than to have the code of the contract readable, because now people would not have to read the code. They only would need to read the properties that are ascribed to the contract, and then next to it they will have a certificate which is essentially a piece of text that can be run through the software known as certificate checker and make sure that the contract indeed satisfies these properties that are ascribed to it. So this is pretty much like a literal certificate that we have implemented. So we have more automated analysis on which we work with the Swiss startup Chain Security. All right, so I think we're approaching the end of this talk. Let me conclude. So there's designing a programming language for safe and scalable smart contracts from the first principles was quite a roller coaster. So, and it was a mix of excitement and angst for the design choices that we have made. All right. And one of the key insights that enable it is the science of functional programming. So that's like, if you know languages like OCaml and Haskell, usually gives you some good ideas how to keep your language minimalistic yet expressive. So the language inevitably will grow and change, and this is something that we had to embrace. So we eventually engineered the process in which we can add more features to the language without breaking backwards compatibilities. And finally, well, there is a lot of excitement about computer science in general and how it enables cool things using deep learning and whatnot. But computer science has many cool areas, and programming language design and programming language research is one of them. And actually has some really good ideas that were there for quite a while and then can be reused with a very low implementation overhead to enable safe and secure decentralized applications in the future. And well, it was very nice to have it is very nice to have an enthusiastic developer community that provided feedback and allowed us to make more informed design choices. This is the web page of the language. This is the paper that you might want to read if you want to understand, like, know more about the principles from which the language has been designed. And this is all I have. So thank you so much for your attention. I will be happy to take any questions.
Thank you so much, Prof, for the amazing presentation. Does anyone have any questions? Please ask.
All right. Well, you know my coordinates. I'll be happy to talk to anyone who is interested more in this technology or its applications or anything about design and programming languages.
Thank you so much.
Okay, now we have 5 minutes break till the next talk. Thanks, everyone.